Recording is rolling. Recording's rolling.
Here's a ball. Hold it up here. And the ball is hanging. Now what I'm going to do is I'm going to pull this string. Bam, 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 harder, 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 until either this string or this string's going to break. Which one do you think will break? I'm pulling that down. Don't I exert a tension in the string? Doesn't the string get tight? Huh? Wang, huh? Doesn't this one get tight too? And so I have a tension here. I also have a tension here. The string is stretched out. So as I pull gradually, which one's going to break, gang? Top or bottom? I want to say the top because I got another string here for the next trial. Let's watch this. It was the top. Because of the weight of the ball or because of the inertia of the ball? Check your neighbor and see if your neighbor sees which of the two properties, weight or inertia, made the top string break. Go. Why did the top string break? Because the weight of the ball is acting up here too. So the weight of the ball pulls on the top. The weight doesn't act on the bottom string. So I've got the weight of the ball pulling on the top string and the tension with which I pull on the top string. Both these, quit, boom, it breaks. But how about now I take the string and I whip it down quickly like that. Why did the bottom string break? Because of the inertia of the ball or because of the weight of the ball? Check your neighbor. I can show you that with this elastic game. This elastic. If I pull, I can pull. Look how much that thing's stretching. Okay, but let's suppose I just go like this. Notice that? There was not as much force up here. The elastic didn't stretch as much when I pulled quickly. That force was not transmitted up here. The inertia of that ball, it wants to sit right there, huh? And I pull, it stays right there. Another word for inertia is lazy. The ball is lazy. It tends to stay doing what it's doing. You got neat?
So it is Friday, September 26th. I'm going to do as many puzzles and demos as I can with you guys. Right, so you guys chapter 4 or 5 puzzles. Here, let's put the due date next Friday. So 1 week from now. So it's be October 3rd. So do any 10 from here. And I went through this morning and I found 2 that I thought were pretty good. So I'm going to recommend these. And I'll go over, I'll point them out to you guys. So if you have this with you. So this is your chapter 4 and 5 puzzles. Like if you just do 10, maybe I recommend these here. Okay, so there's number 9, one that involves a salvage boat with sunken treasure. There's number 5. Yeah, so the numbers aren't really making sense. So just go with it. Number 5, we got a 5-kilogram object. Oh, one, a couple of strings. You guys remember last week we did one like this? Right, there was like a couple of ropes, something like that. Okay, next page. We got a number 11. There's a car with this initial speed, but it's breaking to a stop. Okay, what are the forces involved there? There's there's a number 26 elevator, a guy in an elevator. Actually, we're going to do one today that's similar to that. Okay, so an elevator example. Number 23, a skier on top of an incline, a smooth ski slope. Actually, this one right here kind of reminds me of your car and incline lab. Remember a car to zip it down an incline with no friction? Maybe something related to that. Okay, got an incline. This one, number 1, I got a block with maybe some, it's got a massive, it's got a coefficient of static friction, a coefficient of kinetic friction. Maybe how much force would you have to put on to get it to go? I think you guys will see that concept show up later today. We'll do something like that. Then on the back, there's a few good ones. I got an incline Atwood, so this is number 19, combines an incline and an Atwood. I'll do one of those with you guys today. Number 35 down here at the bottom, athletes jumping into a pool. Okay. Number 26, we got a block sliding, has some initial velocity, but there's some friction, so I think it's slowed down. Okay. But it does fall over the edge of the table and turns into a projectile. And then down here, number 8. Here's a fun question that involves raindrops and drag force. And really, I'm asking this question because it has to do with proportions, right? So there's no numbers with this, but there is an expression that involves proportions between variables. Yeah.
We only do those ones?
Yeah, if you just do those, that's fine.
Okay.
Yeah, that'd be right. All right, so there you go. So that's what I'm recommending right there. Alright, so my earlier AP class, I was able to fit two in. So here, I got some relevant posters today. You guys remember Newton's second law of motion tells us how much something accelerates. You identify what is the net force, as if it's a single force, divided by the mass, it'll tell you the acceleration. We're definitely going to be using that today. We'll do an elevator example. Right, so if someone's say accelerating upward in an elevator, right, how do these forces compare? Or if you knew these forces, what would the acceleration be? Okay. Guys, you guys should be able to derive this from scratch. Of course, you guys have this, right? And we're going to do a similar type example today. Okay. If the elevator is accelerating down, it looks like this. Up looks like this. Constant velocity could be an example of equilibrium. That might be the middle one. Okay, we'll look at we'll bring in some friction today. Right? So not with the elevator, of course, but I'll bring in we'll do an incline Atwood and I'll throw in some friction. Okay. Okay. All right. So we'll be doing all that. So let's start with an elevator. Elevator. Right. So right, so we're going inside this elevator. And let's throw a guy on a scale. So this guy is standing on the scale in an elevator. Okay. Let's say this guy has a mass. So the mass of the person is 60 kilograms. Okay. Here, I'll give you guys Earth gravity is 10 meters per second squared. Okay. And let's say the force rating from the scale. And guys, if the force rating from a scale, what kind of force is that? It's not a friction force, it's a what force? What force holds you up from a surface? Normal. Yeah. So the normal force rating on the scale, force normal scale, just to really emphasize that. Let's say it's reading like 700 newtons, maybe something like that. Okay. Okay. So these are your given values. Oops. Call those givens. Okay. The question is, what is the acceleration? Here, and we'll come up with some follow-up questions. How about some kinematic connection? Okay. What is the distance moved after, let's say, 2.0 seconds if start from rest, so if v naught equals 0 meters per second? Okay. And what is the speed at the end of this interval? That's a after the 2-second interval. Okay. All right, so you guys got that? Got all that? Okay. All right. So while you're thinking about that, jotting that down and get that in your notes. Guys get your notes. Okay. Okay. So big picture is that this has everything to do with Newton's second law of motion. Okay. And really we're going to be doing a version of this right here. Okay. In fact, isn't that the free body diagram? Right there? That's the free body diagram? Okay. So let's go with that from scratch and basically figure this out. Okay. Okay. So that's root map here. Okay. Let's make a free body diagram on this guy. Put a center mass right up there. All right, so one force on this guy could be his weight pulling straight down. So I'll call it mg. Okay. Right, let's go ahead and throw in a number while we're at it. If he has a mass of 60 kilograms, we're calling Earth gravity 10 meters per second squared. How many newtons of weight is that?
600.
Yeah, 600 newtons, right? Okay, so you say he weighs 600 newtons. Okay. And the normal force from the scale, should I drop that as larger or smaller than 600 newtons? It's got to be larger. Actually, I told you what it is. I told you it's 700, so that would be just draw it larger. Call it normal force, and that's 700 newtons because I gave you that. So that's the setup right there, isn't it? Free body diagram. FBD, free body diagram. Okay. Now, can you use that to calculate the acceleration of the elevator? Okay. And to do that, what are you going to set up? How are you going to get it set up to solve for acceleration? Acceleration equals what?
F net divided by F.
Yep. Net force acting on the mass. That's Newton's second law. Newton's second law of motion right there. Right? That feed right into Newton's second law. Right, so I want to know the acceleration. So what do I put for net force?
700 minus 100.
Yeah. There you go. All right. So 700 newtons minus 600 newtons or 100 newtons. Right. That's where that comes from. Okay. If this was APF or Q, I would put in the step show like where I would be getting 100 newtons from would be a good idea. Okay. And acting on how much mass? 60 kilograms. Okay. Is that true? So 100 over 60. See what is that? 100 over 60. I'm getting 1.67 on my calculator. Let's do acceleration is 1.67 and 1.67 what?
Meters per second.
Meters per second squared. There you go. Oh, maybe you should specify a direction. Will it be which direction?
Up and down.
Yeah, upward. There you go. Because isn't there more force up than down? So overall, with the upward acceleration, right? Isn't the net force and the acceleration don't they have the same direction? Sometimes you'll see little vector arrows above the vector quantities, not the math, but the force and the acceleration. Right? Is that true? Yeah. All right. So you guys go with that? Now, guys, suppose you were inside the elevator just this moment. Like maybe you just woke up from sleep and you feel like, oh, hey, I'm heavier than I normally am. Hey, I'm pretty sure I'm accelerating up because I know I normally weigh 600 newtons. I feel like 700 newtons. Backs up the scale does. Okay. So would you know if okay, we all know the elevator is accelerating upward, right? Okay. If you didn't have any prior knowledge before this very moment, would you know if the elevator is moving upward? Does it have upward velocity?
No.
Okay, yeah, you can't know. It might be because it might be if it is moving up, it's moving up how faster, faster, slower, and slower. Yeah, faster, faster. Yeah, it could be going up faster, faster, faster. In fact, if it starts from rest, that actually would be the case, wouldn't it? It's moving up faster, faster, faster. Okay. But what other scenario could also result in this exact set of numbers?
Slowing down, going.
Exactly. Guys, could the elevator actually be moving down, slowing to a stop? Right? It could be because that would be physically identical. Here we go. Right, it's this one here, right? Could be moving upward faster and faster. Or could be moving down, slowing to a stop. And you get the exact same reading on the scale, wouldn't you? Yeah. All right, so let's have the case where he starts from rest, therefore he's moving up faster, faster. Okay. So how about follow-up questions? As what distance after 2 seconds? Now, if you want to know a distance after some time interval, starting from rest, that's a job for which one of these three amigos? Distance as a function of time. Yeah, first one, right? If he starts to rest, can I just bump this term out? Okay. Right. Hey, it's the college equation. College, oh yeah, college equation. Okay. So let's go. How far it goes is starting from rest, 1/2 at squared. Okay. Okay, so that looks like 1/2, 1.67 meters per second squared for 2 seconds. And don't forget to square the time. Square 1/2. I'm looking at 3.3 meters. Okay. So that whole movement in 2 seconds. So he's accelerating up a little bit, feels his weight go up a little bit. Okay. For 2 seconds. He's kind of a little over 3 meters in that time. Okay. And the other thing I want to know is how fast is he going at the end of that interval? So which one are you going to use to figure out how fast he's going? The
middle one.
Okay. Yeah, you could use either one of these. You could, as a function of 2 seconds time, you could use this one. Or as a function of 3.3 meters maybe distance, you could use this one. They'll both tell you the same thing. Yeah, they both tell you the same thing. Okay. Here. How about this? Let's try it both ways. Final velocity equals a times t, or final velocity squared equals 2ax. I could do it either way. I'll get the same final velocity. Okay. Okay. So starting from rest. So V naught is 0 meters per second. Okay. So let's go. What was it? 1.67 meters per second squared. We're doing that for 2 seconds. Okay. So 1.67 times 2 is 3.3. Well, I think if I take more digits, 3 meters per second. Okay, sorry, I did not need to make the numbers all work out to be the same number. Oops, sorry about that. You guys know these are totally different concepts, right? with different units. So oops, okay, this guy. Was anyway. So it's gonna be square root of 1.67 meters per second squared. Now this would be for 3.33 meters distance moved, right like that. Right. Now I should get the same thing. 1.7 by 3.33. Yeah, 3.33 meters per second. Okay. Get it? Right, so he's moved this far. At the end of that interval, he's moving this fast. Sure. Right. What about at that moment? What if the scale reading goes back to 600 newtons? Right. Right. So he feels his weight drop a little bit to his normal level. Okay, now I'm back to 600 newtons. At that point, what is the elevator doing? Yeah, going up at constant velocity, isn't it? Now we're in this case. It's going up at constant velocity. Aha, aha. Okay. All right, so you can just keep going. All right, so you guys good with the elevator about? All right, let's do a real involved one right here. We're gonna do this one. Right, you guys ready for this one? So tell you the story before I throw any numbers at you guys. Okay, so we'll have an incline Atwood. I'll give you guys a couple of masses, and one thing you have to figure out is like, well, which way do you think this is going to go, like clockwise or counterclockwise? Sometimes you have to like make an educated guess and run with it, and just take yourself along the way. I'll also throw in some friction. Right? Now, in that case, there will be either three forces or components that really matter to drive the system from a whole system approach. See, I put down here a whole system approach. Right? There are a bunch of forces flying all over the place, but there are really three that matter. Right? So the three that matter, yeah, I circled them. You see, I dash circled them. Okay. So do you think the weight of the one that's hanging says let's go clockwise? Okay, wants to move the whole thing clockwise? You guys that? Okay. And this block over here on the incline, well, it has weight also, but the full weight doesn't make it go counterclockwise. It's just the sine component. You see the sine component is really pulling it like down to the left. You see that? It's sine component. Okay. And if the whole system ends up going clockwise overall, let's say this pink one is like really heavy, then wouldn't the friction force also be down to the left on this incline because it's trying to resist the motion? Okay. Okay. So these two circled say let's go counterclockwise, and this one over here says let's go clockwise. Okay, so yeah, it's about between this. Okay. Or if you switch it the other way around, because what if I make this green block really, really heavy and this pink one is kind of light? Okay. And so overall it's going counterclockwise. What would happen to the friction force? Would it reverse direction? Right? So this friction force might reverse direction if this whole thing is actually scooting the other way. Okay? Can we keep track of all that? Okay. So we're going to do that. Now, there's some other forces here too. There's the tension force is just internal to the system, just holding the blocks together. Okay. Now, guys, is this force pulling up on the pink block and this force pulling up on the green block? Tension force? Is that same tension? Yeah, as long as you have like a massless frictionless pulley, safe assumption. Okay. And this normal force is also, I haven't mentioned this until now, this normal force. Isn't this equal to mg cosine theta? When we eventually get to that. Okay. And we will have to get this because you can't know the friction force until you know the normal force. Right? Because there's a connection there too. Okay, so, okay. You guys ready to juggle all these variables? Ready to go? Okay, so let's do an incline Atwood here. Okay, we'll have incline Atwood. Maybe I want to know what is the acceleration of the system, the downward acceleration of one of the blocks, whatever, right? I'll just say abbreviate sort of like that. Okay. And then let's go back and find what is the tension in the stream. We'll find that after the fact. Okay. There's a couple ways to go about and solve this. I'm going to walk you guys through a whole system approach, right? A whole system approach, which is basically this right here. I'm thinking about tug of war between these three force components, and then I'll consider tension after the fact. Okay? The other way to solve it, if it's not with a whole system approach, here, I'll just tell you guys what it is right now. Okay? The other way that I'm not going to do with you guys is you just hone in on each block individually. So you look at this block, and you set up, okay, I've got two forces on this block, and then you do consider the tension. And then you look at this block, and you consider all the forces that matter. So this and the tension pull the other way. Okay? And then you set up a system of equations. You have this equation here, you have this equation here. and then you get sort of acceleration and tension at the same time. Okay. Right, that would be a different way to do it. But I'm going to do a whole system approach. So I'm looking at this right here. Is this net force? Okay. Here. So let's up an incline right here. Make it real big. Give us this page. Okay, so there's your incline. Okay. Let's throw an angle in here. Let's call this 30 degrees. That's a pretty common type angle. It's good to work with. I'll throw a pulley here at the top. Okay. And then let's get a couple of blocks. So a block right there. Okay. And then about another block right here. Center mass dot, center mass dot. Okay. Connect these two guys with a string. Like that. Okay. Yeah, there's setup. Okay. Right, so I need to give you guys some values. Let's call this mass A. I'll call this mass B. Okay. Okay, so I'll give you guys here, say given. And give you guys some values. Mass A, let's call about 3.0 kilograms. Mass B, how about to be 5.0 kilograms? Okay, okay, I gave you guys theta. Let's say G, we'll just call G 10 meter per second squared. Let's say theta is 30 degrees. I'll give you guys some coefficients of friction. Let's go a mu s and a mu k. Let's say the coefficient of static friction is like about 0.4, and the coefficient of kinetic friction is like 0.3. Okay, just make some values. Okay. Okay, is that all right? Okay. So you're given all this. And that's enough to be able to answer that different questions right here. You guys got all that. All that. Okay, everybody good? Okay, got the setup, got all these given variables, got these two questions. Okay, we'll answer them in this order. From the whole system approach, we get the acceleration. After we get acceleration, we'll consider this other question. What's the tension? All right, everybody good? Everybody good? Okay. All right, so let's introduce a Cartesian system that runs parallel and perpendicular to the surface, okay, so that we can consider the forces on block A. Okay. So from here on out, all the forces on block A will eventually think in terms of this rotated Cartesian system. Okay, see that? Okay. Do you guys do the same thing? You guys do have a ruler within reach, right? Guys, does anybody not have a straight edge? Anybody not have a ruler? Okay, so everybody's got one? All right. So dash dots is maybe sort of like an x-axis parallel and a y-axis sort of perpendicular to the surface. Okay, all right, now let's go put some forces in here. So this block B has a weight right here. I'll call this m sub b times g. Okay. Actually, we can just throw in this number right now. Because remember, this block has a mass of 5 kilograms and Earth gravity. Okay, so that's how many newtons of force right there? 50 newtons? 50. Right, you guys see 50? There's 5 times 10, right? You guys get it? 5 times 10? Okay. Okay. Now, there is a tension pulling back the other way, but we'll consider that later. Okay, so I'll just call it F sub t, and we're not worried about that yet. Okay. Remember, this tension is just internal to the system. Right now, all we care about is it's just holding the system together. It's not an external force to the system, to the two-block system. Okay. How about this mass A over here? It also has a weight. So downward force. Okay. That would be m sub A times g. Okay. And how many newtons would that be? 30. Yeah. Everybody sees 30 newtons, right? You guys all say 3 kilograms in Earth gravity. Be 30 newtons. Yeah, is that true? Okay. Okay, no, there are definitely a bunch of other forces on block A, but before I get to those, I'm going to break this weight into components. You guys see how this weight is not aligned to that rotated Cartesian system? Okay, so let's break it into components that are aligned with the Cartesian system. So that weight on block A is doing two things to block A. It's partially trying to push block A directly into the incline, and it's partially trying to drag it down to the left parallel to the incline. So I'm going to break that into components. I like this right triangle method myself. That's what I do. Okay. Arrowhead. Oh, guys, for this component right here, am I holding my roller parallel to the surface? Parallel to the surface? Are you guys doing the same thing in your notes? Are you also holding your roller parallel to the surface right there? Okay. So I have a right triangle with a right angle right there. Right? I'm not holding my roller like this. Ding, ding, ding. That? You guys see that? Parallel to the surface. Okay. Okay. And then, while we're at it, go ahead and label those components. So if I know this angle is 30 degrees right here, right? 30 degrees. Okay. Would this be equal to 30 newtons times sine of 30 degrees? Maybe I should have asked you guys. You guys would have said that, right? Is that 15 newtons? 15 newtons right there? Is that here? Yes. And this would be the cosine component. So here's 30 newtons times cosine of 30 degrees. Let's see, what is that? It's 30 cosine 30. That's 25.9. Can I call it 26 about? Is that okay? 26? Okay. I'll just call it 26 newtons. Okay. All right, plenty close enough. Let's see here. All right. All right, so now we've effectively replaced this weight in terms of these two components. All right, how much weight is pushing into the incline? How much is deploying along the incline? All right, next. I need a. Ooh, guys, what force is the support force from the surface called? No. Normal force. Normal force. Okay, so that'd be like this direction. Call it F sub n normal force. Okay. And guys, how many newtons is that support force?
26.
26. Yeah. 26 newtons. It's the same thing as mg cosine theta. Isn't it? Right. 26 that way, 26 that way. Sure. Guys good? Oh, guys, is there a tension pulling this block up and to the right? Okay. Again, from a whole system perspective, this is just internal to the system, but we'll go address later. I wonder what this tension is. Right, but we don't know yet, so we'll worry about that later. Okay. Now, guys, if there was no friction at all, suppose these coefficients of friction were like 0, 0, or I have like an air hockey table, would that be all of the forces? And that would be the end of the story? Okay. I think it would be it. Right? Now, the fact that I'm giving you some coefficient of friction means that I also have to consider that. Okay. So, especially if you're given both coefficients, the static and the kinetic, you have to make sure that this whole system is going to be in motion in the first place. Because what if I did this? What if I made the blocks kind of similar to each other? Maybe block B is kind of light, okay, or this coefficient of static friction is very large, like 0.9. Could you come up with a scenario where maybe it doesn't even move? You just like let it go and just like it just like stops. It doesn't even move at all because there's so much friction. That could be the case. So you want to test and make sure that there's enough force in the system to break the static friction. So let's do that. So we're going to consider like this right here. Okay, so is there so much force to overcome the static friction? Like what's the maximum possible static friction? That would be coefficient of static friction times the normal force. That'd be the maximum possible, wouldn't it? Right? If you take this all the way to equals. Okay. So on another page here, I'll say force of friction, static, max. The maximum possible static friction would be the coefficient of static friction, static, right, times the normal force. Okay, and that would be, well, I told you the coefficient of static friction is 0.4. 0.4. 0.4. And I told you guys the normal for, well, we found the normal force, right? We had to do some work to dig that out, but we got 26 newtons. Complete things. Okay, that'd be that. Okay, so the maximum possible static friction would be, I'm getting 10.4 newtons. Right, 10.4 newtons. Right, that's it. Okay. So we have to break this friction before anything else can happen. Okay. Now here's where we're going to make maybe an educated guess. Is what do you think is most likely to happen? Is this more likely to go counterclockwise or clockwise? What makes more sense? Probably clockwise. I mean, I did put a sufficiently large weight over here that's hanging. Yeah, I think it's safe to say. And if that's true, which direction does the friction force point?
Again, down left.
Down to the left. Yeah, because it would be trying to resist that motion. So it'd be going this way, wouldn't it? Okay. Now I'll label that F sub F bar, like a friction force. Okay. But the value I want to hold off on before I label anything. Okay. Now, if it was 10.4 newtons, here I'll do a simplified diagram here. Okay. So I'm just going to draw the relevant forces or components. So I'll draw 10.4 newtons that way. Okay, let's go. I've also got this component here. Ooh, don't forget about the sine component of the weight. Isn't the 15 newtons here also pulling down to the left? Right. So that could also be acting. It's a little dash component, another 15 newtons. Okay, so those are conspiring together. The 10.4 newtons and the 15 newtons are both trying to pull a thing counterclockwise. Okay. And then I got this rope, and then it's connected to this other block. Okay, and okay, there's tensions in the middle just to hold these two blocks together. Okay. And over here, I have 50 newtons. 50 newtons. Right. So, guys, what wins? 50 newtons clockwise or the sum of these two counterclockwise? I think 50 newtons is going to win. Isn't 50 more than 25.4? Right. So 50 newtons greater than 25.4 newtons. Okay. Therefore, we've broken the static friction. Okay. Right. So it's definitely going to slide. So it's not stuck in place. It's definitely going to be moving. So let's go find what is the kinetic friction. Okay. Because now we've gone from moving past this pink box to this green box. Because now it's actually in motion. Okay. Which is less friction, isn't it? Because now the friction, like the kinetic friction, would be the coefficient of kinetic friction times the normal force. And the coefficient of kinetic friction I gave you guys as 0.3. So it'd be 0.3. And then the normal force, same as before, is 26 newtons. We found that. 26 newtons. So what is that? Let's see, what's 0.3 times 26? I'm getting 7.8 newtons. So that's the actual friction force while it's sliding, while it's in motion. Okay, that's what I'll do. And so back over here, I'll label that friction force as being, what was it, 7.8? 7.8 newtons. Okay. Okay. Now I'm going to circle all the forces that matter, all the forces and force components. Okay. So definitely, there we go, use a blacking period. Okay. Definitely this 50 newtons says, let's go clockwise. That one's probably going to win. 50 newtons clockwise. Okay. Then there's this 15 newton component of the weight that's pulling back the other way counterclockwise. And we just found this kinetic friction force that's 7.8 newtons, also pulling counterclockwise. So we've got clockwise versus counterclockwise and counterclockwise. Those are the three forces that matter. Okay. All right, guys, got those there. You guys up to where I am in my notes? Everybody's good? Everybody's good. Everybody's good. Right. All right. So remember the first question we're still trying to chase down is what is the overall acceleration of the system? So if we've got all the forces in place, which we do, and you want to know what is the acceleration, we have to go through what formula? Named after a very old guy. Newton's second law of motion. That's it. Newton's second law of motion. So Newton's second law. So the overall acceleration is going to be, it's a fraction. It goes what over what? There you go. Net force on total mass. Right, net force on total mass. Right. So let's figure that out. So a big old fraction up here. It's a big old fraction. Okay. And here, try to put this all on one screen if I can. Guys, what do I plug in for net force? Yeah, 50 newtons clockwise. Yeah, minus. Would it be that right there? Okay. So clockwise minus the 2, counterclockwise. Okay. Right. That would be the net force driving the system. Right. And how much total mass is being moved around? How much total mass? These two guys right here, 3 and 5. So that's 3 kilograms and 5 kilograms for a total of 8 kilograms. Okay. So we've got this net force, whatever that comes out to, acting on this total mass. Right? Just like that. Yeah.
So like you're subtracting the force that's like acting on one way and subtracting it from the other force that's like actually the other way. Like,
Yeah.
I can't read
Okay.
it from your free fall.
Right. Because the idea is the particular approach that I'm doing is I'm not looking at the individual blocks like alone. Okay. I'm looking at this whole system. You guys see this whole system right here?
Mhm.
Okay. So from a whole system point of view, actually this is what we just did for the numerator of that fraction. Okay. So the net force acting on the whole system is this weight pulling the whole system sort of clockwise. Okay. And subtract off these two right here are pulling back the other way. Right? Right. This is on the two block system. Like those are the external forces that matters. It's the three that I circled here. Boom, boom, boom. Okay. Okay. So while you're digesting that, I'll just point out some other things going on. Okay. Yes. Oh yeah. Go ahead.
I was just wondering, after the static friction is broken,
Huh?
does it become irrelevant?
Yeah. Okay. Yeah. So after the static friction is broken, is all the static stuff irrelevant from there on out? Yeah. So now we're just focused on the kinetic friction. Okay. You just want to check the static friction to make sure that it's not just stuck in place. Okay. In this case, what it's going to be. Okay. Yeah. So there are other forces. Like there's this normal force that's canceled out by this mg cosine theta, so that doesn't matter. Okay. There's the weight of this block, but we already both had the components, and from here on out, we're just thinking in terms of components. In fact, one of the components does matter. There's these tension forces, but that's just internal to the two block system. It's just holding the system together. Kind of like if I'm like pulling on this pin, I think there's some tension between the plastic molecules holding the pin together, but it's not a net external force, so it's not actually moving the pin, right? It's just holding the pin together. Right? That's kind of what those strings do. Okay. So it's a two block system, okay? And we're looking at the entire system, hence the whole system approach. Okay? So it's these three forces that matter. Okay. And that brings us to this right here. So we've got this going on. Calculator time. So the acceleration then would be, here, what's 50 minus 15 minus 70? I'm getting 27.2 newtons force acting on 8 kilograms. That's 3.4 meters per second squared. All right, so that's the rate the whole system would be speeding up clockwise. 3.4 meters per second squared. Okay. Okay, you guys got that? Okay. The other question was, what's the tension in the string? So to get the tension in the string, now we're going to have to go more specific. We're either only focus on block B or only focus on block A. Okay. Guys, which one do you think is usually easier to work with?
Block B.
Yeah, block B, because it's only got two forces on it. So let's start with that, and we'll go back and we'll check with block A and just make sure it's the same thing. I think it will be. Okay, so from the point of view of block B, we'll also set up the F net equals MA, but we'll do that for block B. And on block B, the forces are, well, let's see, if it's accelerating down, then I'll call it positive, so I can have a positive acceleration. So it'd be 50 newtons. They're pulling down minus this tension force is resisting it, and we're solving for the tension. That's the net force. 50 newtons minus the tension is the net force. That's making this block B, which is 5 kilograms, so 5 kg, accelerate at, and we just found right here, 3.4 meters per second squared. 3.4 meters per second squared. Okay. Is that true? Just like that. Okay, so now we can get the tension. All right, so let's see, add T over, subtract that over. So the tension would be whatever 50 newtons minus 5 times 3.4 number of newtons would be, kilogram, meter per second squared, whatever that is. So 50 minus 5 by 34. I'm looking at the tension force I'm getting is 33 newtons. 33 newtons. Right. Now, last check on this is if that's true, then that 33 newtons should also be applying to block A, shouldn't it? So I'm going to put that 33 newtons tension force on block A, and I'm going to check to make sure that the acceleration still comes out to 3.4 meters per second squared for block A, because it's got to, right? These blocks have the same magnitude acceleration. So let me try that. So looking at block A here. Now block A, Here, I'll give a simplified diagram. Right. Has a bunch of forces on it, but in the direction of motion, there's these two saying let's go down to the left. So that's like 7.8 newtons here, and well, 15 newtons here. Okay. And I just found the tension is 33 newtons the other way, 33 newtons. Okay. So it looks something roughly like that, right? I know it's real chicken scratch drawing. But let's see what would the net force then be, and therefore what's the acceleration? So acceleration is net force on mass. The mass of this block was 3 kilograms. Remember? Okay. So that would be 33 newtons minus 78 newtons minus 15 newtons. Okay, so this only pertains to block A. Acting on block A of only 3 kilograms. Okay. Isn't that specific just to block A? Okay. Okay, so let's try it. 33 minus 7, 8 minus 15. All collectively divided by this 3 kilograms. Okay. Hey guys, if you're following, make sure you guys are following. I already know what the answer has to be.
No.
Guys, what does this answer have to be?
3.4.
3.4. Yeah, it's got to be 3.4 meters per second squared because that's what it was for the system. That's how we were able to find what is this tension in the first place. Right? Okay, so here, backtrack a little bit. So we found the acceleration for the whole system. Therefore, that would also apply to each individual block. Okay? So we went through block B and said, okay, therefore the tension must be this. Now we're applying that tension over block A. And if everything checks out on block A, this has got to be 3.4. Okay, so it's got to be. It is. It is 3.4 right there. Meters per second squared. Huh, so check. And we're good. Good. Because it had to be that the whole time. All right. All right, so that's as far as I got over today. Oh, I got a perfect amount of time to play the Principals Friday message for you guys.